Hello, everyone. Please excuse my husky voice. I have a cold. I'm really pleased that Chuck is here for us today. And a few small things I can say about him is a very distinguished career. But in architecture, let's say in the last 10 to 12 years, we've become very used to the words transformable and adaptive. Chuck is really the leader in this field. And there's a body of work that goes back almost 30 years of mechanical and dynamical systems. And he has a particular genius for not only just inventing them, but bringing them into being, bringing them to market in the case of the toys, and in the larger structures, realizing them. And the work is very well documented on his website, but we're pleased to say most of the things that you will see today are not on the website. So particularly for those from EmTech and our companions, Chuck has been an inspirational figure for us for component systems and movable systems that we have worked on for 10 years or so. And I think his influence in architecture is very widespread across the world. So please join me in welcoming Chuck Hoberman.
Thank you, Michael. It's great to be here, to actually be back at the AA. I think I was here 6-7 years ago. And in the same way that maybe some of the folks, students here and faculty looks at my work, I like to look at what's happening at the AA as well, which is it's very exciting. And I do see some really fruitful lines of influence that are going on, and maybe back and forth as well. I have a practice in New York City, small practice, which is a design and engineering practice. And we've basically characterized what we do as working with transformable design. And to this group, I don't really even need to define transformable, but I will because it's part of how I frame my work. But for me, transformable is making objects, and those objects could be toys or stage sets or products or artwork or even buildings that change their size and change their shape physically and in real time. And these are some of the projects, transformable projects we've done over the years. And our idea is not necessarily just saying how do I get from A to B, but what really is all the in-between states, the process of transformation, the qualities of that. And I'm going to talk about this in a number of different ways. So we might start with this concept of size change, shape change, transformation in nature. And if we look at water flowing or clouds morphing from one shape to another, this is kind of the idea of what I aspire to in design. Or maybe beyond something like clouds, more intentionally, we might think about organisms where there's almost not an intentionality. We know there's no intentionality to evolution, but there's a kind of a direction to how shape change and size change fits into the larger evolutionary program of adaptation. And of course, it takes a very long time for species to change their form and adapt from one stage to another. Or we might look at how organisms change within their own lifetimes, the morphology of an embryo changing, we're all changing size and shape, birth to death. Again, that's the kind of qualities that interest me. And then you have these examples in nature which are really, very fantastic. This is a kind of a cephalopod or cephalopod, I think, an octopus that changes its size, shape, color, texture, all with the intent of kind of grabbing little fishes as they swim by. And as a designer, I think about, what if we could design things that transform like this, the way they do in nature? And of course, designers do design things that transform all the time. Really towards the beginning of my career, those first animations of shapes changing into other shapes. Terminator 2 was a real big one for when that first started to appear. But now we can design transformation, but not generally in the digital world. It's, you know, it's virtual, not physical. So we might look at a kind of a little schema where you have natural transformation, which is physical. You have digital transformation, which is designed. And what I call transformable is the kind of merging of those two. It's physical change, but it's designed physical change. And really how to do that in as broad a vision as possible. Just a new level of design. So I am, by training, a mechanical engineer, also a sculptor, but I love mechanisms. And one of the things that I love about mechanisms is their tactility, the kind of the touch qualities of how they change, you know, beneath, you know, in sort of manually and with hands. But also that the way the mechanisms are very physical, but at the same time, there's always something kind of ineffable about them, and that non-physical quality is the motion itself. Motion isn't really a physical quantity, it's about changing relationships. And for me, mechanisms, you could define them as an embodied system of relationships. And that really is, you know, the kind of, it's, designing mechanisms is something that is, you know, it's a tradition of design that goes back hundreds of years. And it's something that I love. So we might start with basic paradigms of what these things are. Traditionally, the way that you think about these engineering paradigms, and it still is true today in engineering schools, you have structural engineering and you have mechanical engineering. A structure, it's all about like what an object does in relationship to forces. A structure will resist forces, but a mechanism takes those same forces and converts them into motion. So that's a kind of a dividing line, but of course it's somewhat artificial, because when we make something, structures always move at least a little bit, and mechanisms have to resist forces as well. But then within mechanisms themselves, again, this is a little bit on the engineering side, traditionally, you know, when I studied mechanical design and studied kinematics, the whole idea of designing a mechanism was to design a motion path, to design a trajectory. The mechanism as an object wasn't really the point. It was what it did. And this goes back to what our definition of a machine is. It's there to perform tasks, not just to be as a kind of a designed object. And what you'll see in the work that follows is a different paradigm for a mechanism, which is transformable. In other words, it's focusing on the object. The function of the object is to transform itself by itself. And over the years, this idea that really I have been working with now for decades is something that's been implemented over in a wide variety of scales at a wide variety of sectors, from miniature medical instruments up to architectural scale, with a lot of continuity of the concept through all of these different applications. So I'm just on the small scale, this is some work that I've been doing with the microrobotics lab at Harvard to make mechanisms that are in the sort of millimeter range, and this is a little Hoberman linkage, about 8 millimeters across. And then at the other range, a project which we'll talk about a bit more, which is a retractable roof that we're working on now. Scale of the stadium is about 140 meters. The roof itself is about a third of that span.
You guys can get your own shot.
No, don't worry.
Hello.
You should, because I'm terrible at sending stuff.
Wow, we have a soundtrack. Do we have an AV person in the room?
So,
My phone is
Peter,
off.
you perhaps better than anybody.
It
Yes?
sounds like somebody
Yes.
who works
If
for
you
me, though.
see this, this is where the
Honestly, it does.
This panel has not been screwed down.
Oh,
Guys,
I see. I see. It's the video. Okay, I'm going to turn the sound off. That's what it is. But the odd thing was that there was no. Oh, I know what it was. There's a stray video. All right. Don't worry, guys. I'm not mad. Just slightly. I'll just delete that. It's off to the side. So the thing that's kind of you know, honestly speaking, it's striking is that the actual design of this object and this object in many ways is not dissimilar at all, and yet there are whatever these 3 or 4 or 5 orders of magnitude of size between them. So they're principles that are carried over, very, very different scales. As a designer, somebody who was originally trained as an artist and has gone on to work in engineering, I look at all of these as very creative directions and options, and that there's a kind of a continuity between the work of an artist and the work of a scientist. And in between is this idea of invention. And I am an inventor. I have patents. I've always liked the idea of invention. And when I think about invention, I like to look at what people have said about it who are inventors themselves. This is a quote from a French mathematician from the 19th century, which I love. "Thought is only a flash between 2 long nights, but this flash is everything." And that's it. That's the aha moment. That's the light bulb moment. That's one of the things that I love about what I do, is there's always that chance that, you'll be stepping out of the bathtub or whatever, and something pops into your mind. So I'm going to talk about one invention that I had that goes back some 25 years or so that really informs a great deal of work since then, but it was something that really came in a flash. And I'll show you a little movie of this, and I think that you'll get what it is pretty quick. So if you have a scissor link and the 2 scissors are straight with a connection at the midpoint, you get 2 parallel lines at their edge. If you move that connection off of center, you get a changing angle between them. And my discovery was that by bending or angulating those links, the angle no longer changed. That was the invention in a nutshell. And by doing that, I was able to create a ring that would open and close, and many, many other things besides. And I went and I think I'm going to turn this off, even though I have one slide I want the sound on, but just go from there. I patented it in 1990, the invention. This is the underlying invention for the toy, for the sphere, and began to build structures based on this idea, an expanding dome from about 1991. And then, of course, the toys themselves, which you see here. A lot of people are familiar with this. Bear with me just one second. I just want to now introduce our UK spokesman from Ashburn, and I'll just let this play for a second. So adults like these things too. And there are a lot of other ways to play with spheres. This is not something I'd suggest trying at home. But look at that. I mean, what you're seeing is, if you just kind of think about it kind of like in your body sense, in your visceral sense, you see the weight of the body, you see the sphere opening. It's very legible what's going on, how all the forces are being transferred. And I really want to talk about that physical quality of designing these things, which is very close to kind of the conceptual insight to design them. This is a way that I've worked with, in a much more practical sense, these transformable ideas. It's a shelter for crisis relief and military use that I invented with my lead engineer, Matt Davis, a few years ago, and has been licensed to a tent manufacturer that has the Eureka brand. So this is about a 70 square meter tent that goes up in about 3 minutes, and thousands have been made and deployed around the world. So in this case, it's really trying to work in a very practical, physical way with a few people to get up a shelter very quickly that also is very strong for wind and snow loads, et cetera. But the other side of this kind of physical reaction to these things is you don't necessarily need to touch them. I've done a lot of work in science museums for kids, and you just watch what these kids, their expressions and their gestures when they're seeing the sphere open, and it's because they're feeling it in their bodies. And I've seen kids literally just fall backwards when they see one of these things opening in front of them because they feel like it's hurtling towards them. And there's something just very intriguing about that, these sort of physical responses to transformable objects. As an inventor, what I try to do is not to invent devices, but to invent classes of devices, to invent sort of mechanical typologies, if you will. And this is one of, out of the kind of short linkage video that you saw in the patent that followed, this was a whole basis for a whole series of structures that I call shape invariant expanding structures. What that means is that there's structures that get larger, but their shape doesn't change. And these are a whole series of different shapes that I've designed over the years, many of which have been built as well. The spheres that people are familiar with, sometimes they think the invention is the sphere, but in fact, it's the method to make expanding shapes themselves. Making objects that expand but don't change their overall shape and profile has some other interesting qualities in terms of the motion itself, where all points are moving out in straight line trajectories from a center. So there's a kind of a expanding universe quality, and we use those straight line trajectories very often to create support points and motion paths. So this helicoid, this spiral, is held up by a series of straight line cables. And here's another one of the sculptures in this series, a hyperbolic paraboloid, just another mathematical shape, and you can kind of see from the left to the right, this somewhat complex shape is actually just a kind of a pure scaling. And there's a lot of very interesting perceptual things about that type of motion. And here's an expanding dome that's being pulled out. It's about 6 meters across. So one thing that we might think about when we're making larger structures is you're making something that has to negotiate between its motion and its supporting, its structural support. And when you see, so we could say that something's moving from a kinematic mode to a structural mode. What you're seeing here is a dome, like a Bucky Fuller geodesic dome, that has many of the same qualities as a classic dome in the sense that it has the triangles, it has the shape, it has the same ground support. So what's happening here? How is something able to be both in motion and at the same time to be structural? This is me in an earlier day doing some of my hands-on testing. And the reality is that you're only making one object. It isn't like it goes from one mode to the other. It always has to negotiate the way that it reacts to these forces. So in this case, we're seeing a hydraulic cylinder that's pushing up on the dome. We're standing on it, which is kind of like an applied load. And this mechanism has to resolve all of these loads into what we might call a stable process. Usually a structural engineer says it's stable if there's very small deflections. But when you're making a kinematic, a mechanical, a transformable object, you actually want it to move, but you want to move it in a way where it's safe and secure and in some sense stable. So it's kind of moving that idea of stability from a process, from a state to a process. And here's the same dome again as installed in the World's Fair in Hanover in 2000, where it was a kind of a symbolic representation of a historic cathedral powered by cylinders. It's about 20 feet across, made of aluminum. And I'll just show you a few more more recent projects that we're doing. This is a sculptural piece that we made for a couple of collectors in Bordeaux who have a vineyard, and was our first piece that we actually installed in kind of a natural setting, an expanding sphere on the terrace of their chateau. I like this slide because it shows a little bit of the craft of making these things. This is machined aluminum where these grooves have been machined in it to kind of reflect the light and kind of mix the light. But there's an enormous, these are engineering challenges, but in a way they're also challenges of craftsmanship as well, with a lot of attention and focus on detail, on the joints, on the connections, on the actuation, and making all of these work as a system so that something like this can be installed, and in the same way that we're in a place where these buildings have lasted for hundreds of years, that something like this may not last for hundreds of years, but at least maybe for decades. We've done a series of projects for live entertainment over the years. These tend to be a little bit intermittent and large scale, but they're some of the more exciting projects that we've had a chance to do. In about 2001, we were invited to build a structure for the Winter Olympics in Salt Lake City as a kind of a curtain where they gave the medals out every evening. So this was the Olympic Arch for Salt Lake City. And here you see it's about 72 feet across. And this was during the testing in Salt Lake City. So one thing I think about when I look at this video is standing in kind of the freezing temperatures of Salt Lake City with, the winds blowing. And there's a moment where you're taking this thing, which had been tested. This shows the indoor testing, which had happened earlier in New York. But there's a moment where you press the button, and it's terrifying. And, your teeth feel dry, and you just don't know. But it is that sensation, which I think is, it's the mood, it's the sensation of innovation, of having done all of this preparation and calculated all the risks and everything, but still you're pressing a button to say that 15,000 pounds is going to move a particular way. And it's exciting, and it's really kind of like what myself and my team really are all about, is really going after those opportunities. So this particular piece is made of aluminum. It's a series of panels. Each panel is about 4 by 8 feet, like a sheet of plywood. It's aluminum extrusions backed by a polycarbonate backing. And so during the daytime, you kind of look at it and had a fairly kind of tough industrial look. But then they would light it. This is 2002. They didn't have all the lighting options that they do now, but it was still these sort of color kinetics, multicolored lighting, and the way that the Lumicite material took the light was fantastic. And then in the evening, it became part of the nightly show where they gave the medals out every evening, and you can see it opening here. So there was music, dance, the lighting. When the curtain first moved, there were some 20,000 people in the audience, and they really didn't know what to expect. Maybe they had seen it before on television, but they really, when you see it for the first time, and it had all been choreographed, so there really was this audible gasp when it first started to open. Really terrific project. And then more recently, we had another superlative project, which was designing a transformable video screen for U2 for their recently completed U2 360 tour. And I'll take you through this project a lot, which was really, amazing on a lot of different levels. By the way, did anybody see the U2 360 tour here? Always curious. One? Okay. The idea for the tour, it's an arena tour that traveled around. There's a big superstructure, which they called the Claw, which they would set up. And there were 3 of these steel structures built. And if you look at the scale, we're talking about not just building scale, but virtually infrastructure scale. This would be set up with a crane, clad with fabric, with a stage which had a lot of really interesting elements, rotating bridges so the band could walk from the inside to the sort of horseshoe-shaped part of the stage. The speakers themselves, these are like a couple stories high. And then our piece was a video screen. So you may ask, what is a transformable video screen? And that was kind of the design brief that we got, which was to make a new type of video screen for the tour. The team who knew my work is up here. That's Frederick Opsimer, who was the LED expert, Mark Fisher. And I was reminded by Brett Steele that Mark taught here, passed away sadly last year. Mark is really a true genius. Anyway, it was a fantastic, fantastic collaboration. Myself and Willie Williams, who's the artistic director for the band. These are early sketches, and we sort of came up with this sort of general notion of a structure that would be kind of high resolution on the left, and then would expand down towards the band at some point during the concert. Through Mark's kind of design guidance, we adapted the shape to this elliptical, conical shape. The blue is basically representing the high-resolution video. It's about 4,000 square feet, and then it extends down over the band, about 25 meters high. This is the manufacturer. During manufacturing, applying some 500,000 individual LED source lights, each about 25 millimeters across. And then this is a film that was made by Barco, which is the LED manufacturer, showing the assembly of the scissors, which are then packaged into these individual units. Each unit weighs about, 700 pounds. There are 96 of them. And they actually invented these robotic forklifts to assemble it in an object that is some 30 tons that is assembled together with all of the electronics and all in about 6 hours, which to me is the most single astonishing fact of this particular project. And then it was deployed around the world hundreds of times, several hundred times, in fact. Really an amazing concert. The screen kind of lived mostly during the concert as just an interesting shaped video screen, but this shows it moving. I think actually this was at Wembley Stadium. And you know, you're looking at something that is 30 tons, 7 stories high, moving in a way that just is, I mean, it's unprecedented. I mean, it really it was a project that, you know, people will point, you know, sometimes people will say, well, how much was it? Well, it was millions and millions. It was probably the single most expensive rock tour and probably the most profitable as well, ultimately. And yet, when I think about like what was built, it was like sending a man to the moon or something, but at like 0.01% of the budget to do that. It was based on just this amazing talent of engineering and design and tech and creative professionals who could say yes to these really crazy concepts rather than sort of worrying them to death where they ultimately would get killed. Anyway, it was really quite an experience. This is a couple of shots from the during the concert. Willie would just use this as this kind of palette that he would paint on. It was kind of almost like a really a work of art in a rock show. A lot of interaction with the band itself. Bono used to call it his spaceship, which if you look at it from the interior, it really does have that feeling. So, you know, where do you go from here? I mean, it's there's really, I mean, this is a project that almost kind of it was really an apex. We walked out, we did it, we kind of stepped back, and now we just sort of wait and see if, I'm not sure whether we'll do more sort of rock and roll sets like this or not. There aren't that many bands that can really make something like this happen. We are working on I want to put a small project in that we're working on now for an entertainment company to make kind of a stage set. I mean, it will be part of a performance which has some things in common. They call it the Lotus Tower, and I just kind of threw it in because it's more recent work. So this is these are showing the sketches from the designer and then how it was translated by my team into a mechanical concept that could be structural and properly controlled. And here's an animation. It's about, I don't know, 13, 14 meters high, it'll be powered by motorized linear actuators. And I mean, I love this kind of like, you know, I mean, I'm actually very interested in this kind of applique of the lotus leaf to the mechanics. That really is something that gets back to my original, you know, I studied fine arts originally, and it's nice to do some things that are not completely governed by the structural mechanical requirements, but that you can start to become more expressive as well. So we're in an architecture school, among other things, and I'll talk about our architectural projects. I've always loved the idea of transformable architecture, really from the start of when I got interested in transformability in general. Again, I'm not an architect. I'm trained as an artist and an engineer, but my dad's an architect, and I'm teaching architecture school. And it was really only in about the last 10 years that I started to have the opportunity to begin to apply these technologies to actual buildings rather than pieces of art or entertainment or sort of symbolic buildings. And this was one of the earlier projects that I worked on, which is the dynamic facade in Tokyo. It's a beautiful building. It doesn't have a lot of Hoberman technology. They're really a series of programmable shutters that open and close, but it was a great opportunity to make kind of a first dynamic facade with a really great design team. Around that time, I began to invent a series of structures that were based more on the idea of transforming surfaces rather than volumes, because when I thought about what's a practical way to implement transformability for buildings, I thought maybe it's the facade. That seems to have more opportunities for sustainable performance and practical installation than making a building that actually does a lot of volume change, which I explored a lot sculpturally. So one of the really early opportunities was with Foster and Partners, where we worked on Aldar Central Market, which is a development in Abu Dhabi. And you know, the Foster team was very open to the idea of using our technology, and ultimately built this roof that's in a kind of a retail environment, a souk, but that's actually an exterior roof in Abu Dhabi that opens and closes with the sort of mixed with the mashrabiyah, the fixed fenestration of the rest of the project, built by a firm out of Dubai. This was a sculpture that I did at the Museum of Modern Art in 2008, which was also an exploration of these surface transformations. And they're made of counterbalanced sort of diamond mechanisms that open and close that are wrapped onto a doubly closed surface. So when you stand back, it almost feels like these diamonds are rotating in and out of the plane, but they're actually slats that are moving within the plane. And in sort of a more imaginative sense, what I'm interested in is wrapping a building with these surfaces that can open and close in very interesting ways, in ways that enhance the function of the building as well. And you can see a little bit more of the mechanical detail here. Another one of the technologies in this series is for transformable screens, which we've sort of named tessellate as a kind of a product or technology. So what you're seeing here, which is, by the way, not an animation, it's actually a film, is layers of perforated metal that are being shifted relative to one another with our patented mechanism, and it creates this kind of kaleidoscopic effect. But it is basically can be installed on the interior or exterior of a building and can be used both for decorative but also for light control and thermal management as well. We work in partnership with a factory in Kansas City called Zaner. They do a lot of really some of the most spectacular metal facades, and you can see here the panels being assembled and kind of hand tested. These are about 5 by 12 feet layers of stainless steel that are, I don't know, about 2-3 millimeters thick individually. And this shows the panels installed at our clients, which is the Simon Center for Geometry and Physics at the University in Long Island, as this is as an interior screen. So it's somewhere between art and architecture. It's not a full-out architectural implementation, but it's a very architectural treatment of a kind of experiential sculpture, and quite beautiful with the way that the shadows are cast and the light. A couple other pictures. We'll just go through a couple more architectural projects quickly. We do have some large projects that are on the boards. They take a while to implement, but I'll introduce you to a couple of them. This is a project in Saudi Arabia, which is part of the King Abdullah Financial District. It's a city that's being built in the middle of Riyadh. There are these developments that we don't see a lot of ourselves, but they're just enormous. And we were invited to join the team that was designing two buildings, which are spas, one for men and one for women, which will be clad with titanium screens, all 4 sides plus the top. And of those screens, about 20% of them will be dynamic. So it's a huge project. Absolutely, it will be a real first of for us. You can see an early animation during scheme design of the external skin of the titanium, and then as it rotates around, you can see its relationship to the glazed surface and the structure that basically both of those hang off of. And here's another part of the animation which shows the interior views. So there'll probably be some questions about what about sand, what about longevity, what about, sort of how do you develop this kind of innovative, technology in the context of a project like this, all of which will have maybe an interesting part of the conversation. But clearly, it needs to be a project with a budget and a client with vision to make all of this work. And in this case, it looks like we have it, although the project has been has not gone to construction yet, but the design is complete. Working with our friends at Zaner, we have built a mock-up. So this is showing a couple of the panels. Again, now the material is titanium, which is treated with a color interference coating. What that means is that basically there's sort of an electrolysis process where it creates an iridescence on the molecular layer of the material, so certain spectrums of light are picked up and it gets this blue cast. And it's a really space-age kind of material. It looks amazing. You kind of get a little quality from the photo, but you can kind of see the blue sort of hovering in between, and then this shows the full mock-up. Part of the concept of this mock-up is that there are 4 static panels and 2 kinetic ones, and what we're trying to do with the architects is create a sense that the overall building has a single continuous gradated living skin, so that basically you can get the sense that the building is alive, but in fact we're only going to have a small portion of it where the actual kinetic animation takes place. We're doing a project in Japan. It's actually the same client that we did the earlier dynamic facade I showed you in the first part of the architectural slides. This one is a much smaller project, but one where we're able to work with Hoberman technology in kind of a new way. And it's a series of external curtains on a somewhat traditional Japanese residence. So you can see here, what they wanted was very large curtains, 4 meters by 9 meters across, that would disappear into the eaves of the roof with no tracks or external supports. And this shows a prototype of the concept where these slats are kind of raised in. So it's, we're hoping we're going to get the green light to begin construction on this shortly. I think this will be made out of perforated metal. We'll work with our friends at Zahner on this as well. The last architectural project I'll speak about is a project for a retractable roof for the new stadium that they'll be building in Atlanta for the football team, the NFL team, the Atlanta Falcons. It's a project that just started in 2013, but it's actually moving on a pretty good pace. So we joined the team. It's a sports architecture group called 360 Architects, and we work with our longtime engineering collaborators at Bureau Happold on this. And the idea when we were on the competitive side was we wanted to come up with a concept that would display innovation on all kinds of levels for stadium architecture. And for those of you who are interested in retractable roofs over Stadia, which is sort of one of the few areas where kinetic architecture is widely accepted, there's been a kind of a stasis in the design of these things for a long time, where basically most retractable roofs are kind of panels on tracks that move back and forth. There might be 1, there might be 2, but they more or less are very kind of pedestrian in design, although very large in scale. So the idea here was to come up with something that would have a more integrated design concept. I don't have the best video, but what you're seeing is the diagrams on top, and that very kind of abstract octagonal shape you're seeing is actually the physical movement of the panels. And here you can kind of see it a little bit more legibly. So we're getting an aperture that's all being made with linear motion. There's no rotary motion at all. But the scale of each of those pie slices, you know, from tip to the first corner going back is about 250 feet. They weigh many, many tons. And we're not the sole author of the concept. It came out of a kind of a lot of team interactions with the architect, with another mechanization consultant, Unisystems, and with Bureau Happold themselves. And this is due to be built in 2016 and would be by far the largest kinetic structure that I've worked on, and one that I think will really kind of like open up new sort of design horizons in Stadia. So it's a very, very exciting project. Now, if you know inventors always are most enthusiastic about what they've been working on last. And so that's what I'm going to talk about now, is as we close the talk, is sort of some new research developments and horizons that interest me, and I hope will interest you as well. So, as I mentioned before, you know, probably the single most seminal invention that I came up with was this way of making expanding structures. But what's always interested me for kind of obvious reasons is not to make something that gets bigger without changing its shape, but could we design objects that we could program them to go from shape A to shape B, but really do it the way a digital designer does, just kind of specify it and then have a technology that would actually physically make it happen. And I can't say I've cracked that code yet, but I've made a little progress and I'm having a lot of fun with it. So this shows more conceptually what we're talking about here, where you could kind of match up any two shapes, which would then bring us into, you know, the original sort of big project, which is how do we make objects that transform the way they do in nature and design them the way that they do digitally. So I was going back through kind of my portfolio of old concepts that had never been built, looking for clues. This was a kind of a nautilus shell that folds itself up on a spiral track. Thought this had a nice shape transformation. I had done some work, I don't know, 5, 6 years ago for a theme park project for these transformable trees, and this was another part of it, of how to make things that were more expressive and sculptural rather than being so highly constrained and technical. And then again, around the same time we were working on U2, I began to explore these spinning forms. So these are like a series of just like posts that are just spinning around, and I'd conceive of them as a kind of a stage set. But they have this very interesting quality of transforming their shape, although the mechanical motion is actually very, very simple. And then this began to develop. I saw another way of making these spinning forms where it's more of a volume that somehow twists itself up and corrugates itself. And this shows the animation and then the prototype. And I really liked this model. I mean, the shape transformation is very straightforward. It's just a cylinder that turns into a sphere. But I began to think about how could I generalize this way of building to make a wider variety of shapes. So this is showing a plan and elevation of an elliptical shape rather than a round shape. And it's, you know, it's a very intriguing motion and essentially buildable, which is always my thing. You know, I mean, these are very abstract animations, but I could build this given some time and money and all that. How do you build these? So one thought was, let's simplify it, and rather than making a continuous surface, we'll just make a series of bent tubes. And this shows an early design for that concept, which is a sphere that turns into a cube. I'll just play that one more time. So a sphere, and what you're actually seeing are rigid objects that are all just rotating themselves around, but the overall form goes from sphere to cube. So that was pretty cool, and we actually have a commission now to build a small one of these, kind of a tabletop. So that will be fun to see that. Other explorations that were done at the time were something that would be a little bit more freeform, that would undulate in sort of more of a 360 fashion. And again, it's all about creating these curved splines and their relationship to each other. How do you make a freeform tube? Well, you go to the factory that makes them. It turns out that there are these machines that basically can bend a tube into any three-dimensional curve you want. So the pressure of the rollers is being combined with a push axis and then a rotary axis on the stainless steel tube itself. And so long as the tube doesn't hit itself, and also there's a minimum bending radius, you can make just about anything. It's a factory in Switzerland that we're starting to work with. We got a commission from a private collector about a year ago to make a couple of shapes. These show two of them, and you'll see them here. So this was the simplest of the, we actually made three of them. The third I don't have in the slides. So this shows our sort of convex to concave. It's 30 identical stainless tubes that are all being rotated around their axis. So the top and the bottom of each tube is collinear, and it's just the geometry of the spin that makes it change. And you get, as kind of a little bit of a freebie, you get a wonderful sort of moire effect along with the form change. And then if you check this one out, just slightly more complex, but again, 30 identical tubes. And it really is like a little uncanny. I mean, I've had people who, I mean, the motion is really incredibly simple, but I've had people who have physically been in the same room as one of these objects and said, how are you making the tubes bend? You know, but the tubes are bent, they're rigid, they're not bending, but it's, you know, it's the way that our eye interpolates it. And taking that same kind of a concept, making it horizontal, we can even make some figurative shapes. If anybody wants a vortex that turns into a car, you can talk to me after the talk. So I'll close with one more. This is an animation that we developed for a sculptural competition, which I didn't win, but the work was fascinating. I'm sure is going to find some life in other projects. So I was really trying to go to that first part of the program for morphing shapes I mentioned, which is how can I make something turn into something else? And in this case, the competition was for an art piece for a children's hospital, for a pediatric hospital. So I was looking for shapes which I thought would read for that, and I thought about making a moon that would turn into a star. And it turns out that when you're designing, if you want to find out, well, what shape of tube will make a moon turn into a star, the curve is defined by the intersection between two surfaces. And I think even without being a mathematician, if you just kind of visualize a little bit, you have two surfaces where they would intersect, they're going to make a one-dimensional curve in space. And there's the curve there. That's a single rigid tube which is being spun. And then when it's joined with 36 other tubes and we spin them, we'll see the moon shape coalesce. And then there's one more trick, which is that taking the whole bottom and spinning this as an array. In other words, it's all the tubes are spinning individually, but the whole unit is spinning at the same time, and then you get your morphing effect from moon to star. So this was a lot of sort of painful trial and effort, but it works, and where that leads is anyone's guess. I mean, I'm kind of think about it on two levels. One is, how do I make more cool sculptures out of free-form bent tubes? But the other is really a much broader question, which is, if we as designers and engineers and creators can design things that transform the way that they do in nature, and according to how design happens in the digital realm with so much freedom, where does that lead in the broader sense? And that's very much what, that's kind of like what I'm about. And I've been lucky enough to kind of pursue this for the decades that I've had and had a lot of fun. So I'd like to end with something. I couldn't really think of what to end with, so we'll just end with that. I do think we're just at the beginning. I think there's a lot that is happening that is going to be incredibly exciting. I'm starting to see among my own peers and students and proteges how these ideas are being picked up and taken in all kinds of new directions. And I hope that some of you will be kind of part of that, advance of the way that design progresses and, has the way that we can innovate and be creative. So thanks very much. And I would be happy to take a few questions if anybody has them. Yes, yeah.
So when presentation talked about the changes. They're all kind of related to adapting to one situation to another in a very quick way. It's not like in the nature where it's from the development or growth or disruption. So I was wondering, would there be a future development that it changes because there's a gradual change in the form of something? For example, a tube station is no longer it used to be like a lot of people used to take that tube station, and nowadays that flow is disappeared because a shopping mall has closed down or something, and with the tube station shrunk or something. So it adapts to the situation it is, instead of just like, oh, I need to adapt to a quick change so that it changes form.
Yeah, I mean, that's a good question and and a comment kind of built in as well. I suppose that you know, a lot of what I'm doing is developing examples, techniques, methods, some of which are within my own projects are directly applied to solving a problem, and in some cases really are more, you know, really more just developing the kind of means and technologies to do it. I think what you're describing is a full-blown application with a lot of complexity, say if we use the tube station, and maybe some of these concepts could be adopted towards that, but I don't pretend that transformable design is the solution for all these different very complex problems. It may be that, you know, some kind of adaptive development of a building would happen in very, very different ways because it's just more practical.
Any other questions?
I'm very interested in the transformable design area, but have you had any personal experience with transformable materials?
With
Transformable materials.
mm-hmm.
So, for example, electronic paint, and I know there are other sort of nanomaterials that move around and change their properties.
I've been able, I didn't actually put slides in on some of the work that I'm doing at universities, but briefly, for those of you who are interested in sort of transformable materials, I'm affiliated with something called the Wyss Institute for Biologically Inspired Engineering. Big name, but Wyss is the donor who gave the grant to Harvard to create this institute. And I work with scientists, some of whom are working on these really amazing adaptive materials that are working at the nano level rather than at these large mechanical kind of levels. I'm not a material scientist, so that collaboration is in some ways as much about applications as about technology, because I can't really, you know, contribute to sort of like the biological conceptualization of how all of this works. But one of the things that's been, I've worked with a lot of scientists there, and one thing that really has come home is that, you know, on a systems level, a lot of what I'm doing, and others as well, but I really do see in my work, it's like you can conceptually apply it to these very different mechanisms and regimes and disciplines. You know, there's a great deal of, you know, understanding that can come about through structures, through kinematics, through the mechanical application of forces, and the Institute is working in a lot of these areas. So, you know, it changes with scale, and it changes with materials, and it changes with all these different phenomena, and yet it's that, you know, as one great mathematician or physicist said, it's that uncanny sort of adherence of nature to mathematics that applies across the board. And so in some small way, I'm just kind of seeing that.
Thank you. Alvise from Aro. Thank you very much. Amazing talk. I knew your work. I particularly liked the explanation of the patent.
Mm-hmm.
And then I saw thank you, the explanation of the patent. And then I saw this, one of the last slides where you explain how you can transform one shape to the other one by crossing the two shapes and abstracting the line. I'm interested of what techniques you use to come to your inventions. The first one I thought it was a physical model, but I don't know. The second one I'm less sure.
How I come to the
What
inventive-
tools do you use? Are they physical, digital?
Well, there's at different tools at different stages. I'm of a generation that was kind of, a lot of my career was with digital tools kind of coming to the fore. And, as in engineering it was it was adopted more quickly than in design. But, I would say that, going back to that Poincaré slide in the Flash is something where it's pre-digital and it's pre-pencil and paper, and it's my experience that there needs to be a kind of a mental event that takes place, which does have a kind of a visual quality, but also is it has an abstracted quality as well. In terms of the scissor, that was very much that way. In terms of the but the morphing tubes are actually had kind of a similar process. Within my own design practice, I'm a little bit of a Neanderthal. I work with 3D AutoCAD, but I do a lot of scripting within AutoCAD so that I can kind of explore some of the algorithmic aspects of design. My team uses SolidWorks. It's a very practical software for kind of developing these engineering objects. It's a whole other topic of just tools and method and techniques. I would say, though, that we're at an extremely exciting kind of new horizon where, designers are now designing by programming, by script, algorithmically. I've seen that movement come. I was a big skeptic at the beginning. I'm not. And I think it's very important that this parametric design takes hold, because it's not primarily, in my view, a technology movement. It's a social movement where it's a matter of getting enough people working with these tools, and it changes how you think about what it is that we make. And so I think it's a super exciting development. Yes.
Okay, I think brilliant lecture, and please join me in thanking Chuck. Big ribbons, it's the biggest we've had for a while.